Okay? So then I set this thing up, and I get negative k lambda over r d plus L, right? And then I'm going to plug in my d plus L minus plug in my L. Right? What do we do with the bounds? Now I've integrated, and I plug them in, right? So I'm going to get, going over here, I'm going to get negative k lambda over d minus negative k lambda over d plus L.
Wait,
Nope, I did it backwards. D plus L and d. Thank you. And then plug in whatever it is you need, because you'll have numbers for all those, right? And that would be the electric field caused by all of this line of charge that I just erased at that point. Once I have the electric field and a formula for the electric field, what can I do? I can find voltage, I can find force, I can find energy, I can do all those things. Yes, sir?
So, would Gauss's law take care of any, like, scenario where the point was, like, if the point was not, like...
Gauss's law is going to work in very specific cases as well.
Okay. So, like,
there's nothing I can do about that.
If the point was, like, up or down from where it is right now?
Yes. If I was to put it, Gauss's law would work. Oddly enough, it would, no, the thing we just did would work here, right? Gauss's law won't work there.
Okay.
Gauss's law will work anywhere here. Okay? But it won't work here. And the only way to do it here is a whole bunch of calculus they're not expecting you to handle. So the only two problems you're going to see is here, where you have to use what we just did, or here, where you use Gauss's law. What we just did probably wouldn't work anyway. We wouldn't want to try it. Okay? And then this in-between zone, if you go to upper division E&M, you can find out how to do that using tensors, which are well beyond where we need to be right now. It's a tensor setting. It's basically a matrix where you do integrals.
No.
And you do an integral math, so you end up with this times this, this times this, this times this. And then if you're timesing, you're talking about integrals and different integrals depending on which thing you feed. And that's only an approximation. The bigger the tensor, the more accurate your estimation is big.
So can you do an integral
So
tensor?
they have computers that do that. Okay, good? Good? Think you can memorize that the day before the test and the day before your AP test?
Yes.
You're doing the next one.
I'm going to have 3 tests that day.
Because you're going to like the next one. It's the best of the 3. No calculus at all. But it doesn't look like it initially. So I've got a ring. Now remember, this is a ring that's coming out of the board, right? Okay, so this is the next one. Got a picture on the back for you. I'm going to take a look. I'm going to use their variables so I don't mess things up. I hate their variables. This is one of the reasons why I want to change this worksheet. I don't like the fact they chose to do it this way, but that's okay. It's just me. Okay, they call this theta here, and this is x right there. Agreed? I'm going to erase everything and redraw. Okay. Does that make sense? Picture make sense? It should be drawn on the left-hand side. If you turn over the page, it should be drawn right there for you.
Okay.
See it?
Sure.
Okay. So, and then I've got my little pluses all over the outside of my ring. And they're uniform charge density, which means lambda applies if I want to make it apply. Okay, so our strategy is going to be the same. We're going to figure out what one little piece of charge does to this. Does that make sense?
Yeah.
And then we're going to sum it up over the whole entire ring.
Okay.
Good? So I'm going to pick an arbitrary piece. I want to pick this little top part because I already drew an arrow to it or line to it. Does that make sense? All right. Now I go to try to figure out how much electric field does it apply at this point here? That's a question. What's the answer? K Q over D squared. Love it. I'm going to call it R squared because we have a variable R squared here. Make sense?
Yeah.
Because that's like field I would cause it there. Now, what's interesting about this is what does the one on the bottom cause? Let's make it blue or some color.
The same.
It caused exactly the same in a different direction, though, right? And here's what's interesting. This one goes up like this one goes down like this. Agreed?
Yeah.
So what would happen because those two forces exist?
Cancel each other out.
What would cancel itself out? Would they completely cancel themselves out?
Yeah.
Wouldn't they just cancel out this piece here and this piece here?
Yeah.
Right, because the up-downs would cancel out because it's pushing down, it's pushing up. But the piece in this direction wouldn't cancel out, right? So each one of these pieces is going to add an E KQ over R squared times cosine theta because of the geometry, agreed?
Yes.
Now I'm going to do cosine theta because it's the adjacent side, agreed? So the far sides cancel out, the adjacent side must be cosine theta, right?
Okay.
Now, the same thing happens here and here, right? Pausing there.
Wait, say that again?
Okay, same thing's going to happen here and here, right?
Yes.
One's going to push it out of the board, one's going to push it in the board. Those will be equal, only the cosine pieces are going to matter. So, now I got my expression, I'm ready to do my integral thing, right? So I'm getting ready to do my integral thing. It's got the integral of KQ, I'll go ahead and mark r to the -2 because I'm pretending like I'm going to have to do this. Cosine theta. And then I'm going to have to go around the circle, which might be d theta or dr. Let's call it dr just for our purposes. Dr is terrible. Let's call it another letter. S. Let's call it ds.
Is that like the?
That's like running around the outside of the circle,
Oh,
Okay.
right? Run around the outside of the circle. Now here's something interesting. Does it matter where in the ring does it change the force? No. So since it doesn't matter, do I have to integrate this thing at all? No, because it does changing, right? We only have to integral when r, when I've got r multiplied by something that depends on r. The electric field for each of these pieces is always going to be the same, agreed? So it doesn't matter, does it? So therefore, I don't have to integrate this. So I don't have to do this ugly thing I was about to do. Instead, I can just write k q over r squared plus all of the kq's over r squared, right? How much this one provides, this one provides. Oh, I forgot my, sorry. I forgot my cosine theta, right? Cosine theta plus kq over r squared cosine theta plus kq over r squared cosine theta plus dot dot dot, right? What are those going to, so the k's are all the same, right?
Yes.
The r's are all the same.
Yes.
The cosine theta is going to be the same for all these. So I can pull all those out. And that means q1 plus q2. What are all the q's going to add up to? What are the q from here plus the q from here plus the q from here plus what is it going to add up to? Q net, the total Q, right? The whole ring, right? So the total, I'm going to call that capital Q. I think it calls it capital Q in the problem. I don't know if it does or not. Yes, the total charge Q. So it's going to be Q, right? So the actual electric field for this thing is just this. Now, there's nothing wrong with that expression, but I'm going to ugly it up a little bit. Oh, stopping.
How do you add all the charges together?
Well, I don't know what, let's say we call this, let's say the whole thing's 20 coulombs, right? If this little piece was 1 coulomb plus 1 coulomb, 1 coulomb, if I add them all up, I get 20, don't I? So that's all we're doing. We're saying add up all, it doesn't matter how many slices, but because it doesn't matter how far, they're not changing how far they are, right? So I don't have to integrate them the way I did the last one, right? Because the r squared is not changing. So each one's adding the same pieces. So I can pull the r squared out, I can pull the cake out, I can pull out the cosine theta. The only thing I'm adding is q's. That's all the q's added up, right? Because they're not dependent on r at all. Now, that's not going to happen in the next one. We'll see the difference in a moment. So far, so good? Okay, I'm going to ugly this up. How do I ugly this up? I like my k, I like my q. I'm going to mess with the r squared and the cosine theta. I'm going to say that that e is also equal to kq cosine theta over r squared. I'm going to note the following. Now, probably I did not give you r squared. Probably I gave you the radius of the ring, which is a, and the distance x, right? So instead, I'm going to rewrite this as the square root of a squared plus x squared, which is what r squared would be, right? What r would be?
Mm-hmm.
Squared times cosine theta. And that's just a squared plus x squared, agreed? What about cosine theta? So I probably didn't give you cosine theta either. Peter, can you write me an expression for cosine theta in terms of a's and x's? Or a's and r's, or x's and r's, or anything?
I don't know.
Here's theta. How do I write cosine? What would cosine of this triangle be?
Oh, cosine theta is so adjacent, so a over r.
Here's my theta.
X.
X over r, right? This becomes x over r. Agreed? And so ugly it up further, because we must ugly things up as much as we possibly can. I've got another, what is r is the square root of a squared plus x squared, right?
Yeah.
Okay. So this is going to be a squared plus x squared times the square root of a squared plus x squared, agreed? And I don't want that either, so I'm going to make it even worse. I'm going to say kq over x over a squared plus x squared to the 3 halves. And that's, generally speaking, the way we're going to end up writing that thing.
What? Wait.
Oh.
This is the 1th power, a squared plus x squared.
Uh-huh.
This is the square root of a squared plus x squared, so that'd be 3.5 powers of a squared plus x squared. Yes, sir.
Where did it go? The square at the bottom? Between the cosine.
I squared the square root,
Oh, right.
right?
Okay,
Because it's
yeah,
the square root of r is a squared plus x squared square root. So if I square that, I end up with a squared plus x squared.
Okay.
Probably should have made the square root of r and put it together, r to the 3 halves, and then pointed out the x squared plus a squared. That would be the way to do that, wouldn't it, Blaze? Man. All right, good? Okay, and I'm going to